All right, so we shall move on to heat conduction and the fluctuation theorem. I told you that the Jarzynski equality can be justified in various settings, and similarly, the fluctuation theorem can be justified in many, many different situations. And this particular situation is one of the simplest, or actually, it's almost trivial. Okay, so let me start from thermodynamics to motivate our study. So consider this typical situation. We have two thermodynamic system, both in equilibrium, but with different temperature. So this one is this at temperature beta 1 inverse. This one is at temperature beta 2 inverse. And I assume that this has higher temperature, this has lower temperature. So this is complicated, but confusing. But this means that beta 1 is less than beta 2. Okay, at time t equals 0, we put them together. Then, of course, there will be some heat going on from hot to cold. So suppose that after some short time t, a very small amount of heat was transferred from left to hot to cold. Okay, and then from the energy conservation, also let's say that the initial energy of this system 1 is U1, and the energy of the system 2 is U2, and then at time t, their energy becomes U2 plus delta Q and U1 minus delta Q. Okay. And now I also assume that delta Q is so small that this body still has essentially the temperature beta 1 inverse, and this still has temperature beta 2 inverse. Then thermodynamics tells you what is the change of the entropy from here to here. Okay, so this delta S is ST, the temperature, the entropy in this state minus entropy of this initial state. And then the thermodynamics tells you that the change of entropy is usually written like delta Q over T, I think you remember. And then in this case, it can be written like this. Okay, now you plug this in, and you see that this one becomes minus delta Q, and this one becomes delta Q. So you can write it in this way. Now you recall that this beta 2 was larger, and delta Q is positive. So this is positive, so the product is positive. You see that the entropy increases. Suppose that this one is hotter than this one. In this case, this becomes negative. But in that case, of course, heat flows from right to left, so delta Q becomes negative. This is negative, so still this entropy production is positive. So that's why we call it entropy production. In this process, entropy always increases. Okay, so this is our motivation. And now let's go to microscopic setting of non-equilibrium statistical mechanics. So as you can guess, we consider two system of particles. So we have one system with N1 particles, the second system with N2 particles. Okay, this is not very important, but x1 denote a collection of positions and momenta of all these particles. x2 denote a collection of momenta, position and momenta of these particles. Okay, and of course, sometimes we consider the whole system. So the coordinate, the phase space point of the whole system is denoted as x. It's simply x1 and x2 put together. Okay, now we consider this the Hamiltonian of the whole system. This is Hx, and it consists of three parts, naturally. H1, x1 denote the Hamiltonian of this part alone. H2 denote the Hamiltonian of this part alone. And H interaction describes the interaction between two parts. Probably they interact with each other through some short-range force when they come very close to each other. So usually this is much smaller than H1 or H2. Okay, now by Tt, I denote the time evolution determined by this total Hamiltonian Hx. Okay, and so Tt of x denote the state of the whole system at time t when the initial state is x. And of course, this can be decomposed into the part describing this system 1 and system 2. I know that this notation is a bit heavy, but okay, to be clear, I denote the x1 part like this and x2 part like this. Okay, now I define a quantity called entropy production during this time interval when the initial state is x. It's simply this. And if you recall our formula, thermodynamic formula for entropy production, this is precisely this. Okay. Here we had the difference in energy. Here we have microscopic description and energy in terms of the Hamiltonian. So this is the final energy of system 1, right? And this is the initial energy of system 1. The same thing for the system 2. Okay. And so this is basically this, provided that H interaction is small enough. Okay. But actually, in the derivation of fluctuation theorem, we do not use assumption. We do not assume that H interaction is small. So that's why I said we don't assume this. But actually, to be physical, I think we should assume that H interaction is small in some sense. So, but I have to say we don't have to assume this in order to do this mathematics. Okay. All right, so anyway, so this is our definition of entropy production, microscopic definition of entropy production. And now time reversal symmetry. I want to assume that these three Hamiltonians, H1, H2, and H interaction are all time reversally symmetric. And of course, this star, I think you remember, means that you flip all momenta, okay? And now I write X prime. I define X prime like this. Probably this is slightly different from before, but okay, so I apply this time evolution map to X and then take this time reversal. And then I call it X prime. Then from what I discussed in page 3.6, this is satisfied. What was page 3? Let me look at page 3. Okay, yeah, this one. Page 3.6 is this one, but probably you'd better look at this picture, okay? If you start from here and you flip the velocity and if you evolve it and then you return here, that is the equation that I was discussing. Where was I? Yes, I was here. Okay, so this is this equation. Then by using this, I can show this symmetry. What does this say? Well, this simply says that if you look at the entropy production when the initial state is X prime, it's exactly the same as the entropy production when the initial state is X, but here's the minus sign. Well, this is very natural. If your entropy increases if you go like this, and then your entropy should decrease when you go like this, okay? And here's the proof. It's very simple. First of all, recall that this is the definition of the entropy production, and I simply copied this and pasted it here, but after pasting it, I just put all these primes here. Okay, now I look at this. This is equal to X prime. So I will, no, this one. This one is this. So you see that this is X star. So this is X1 star. So this is X2 star. And also X prime is this. So you have this, simply this and this. And now we know that we assume that these Hamiltonians are time reversally invariant. So you can just remove this star to get this. Okay. And now this is almost the same as this one, or almost the same as this one, but this and this switched. So everything is switched, so you get minus sign. Good. So this is the symmetry for the entropy production. Okay, what in the initial state? So we want to mimic this thermodynamic setting in which you put two thermodynamic system in equilibrium in touch with each other. And so we assume that the initial state is given by just a simple product of two canonical distributions. Okay, so this one this system 1 is described by this canonical distribution with inverse temperature beta 1, and this one is described by the canonical distribution with the inverse temperature beta 2. Okay, now I'm going to discuss the fluctuation theorem, derive the fluctuation theorem. And first of all, this is our definition of entropy production. And if you recall the definition of prime and time reversal symmetry, you find that it can be written this way. Okay, this is just the definition. And here's the basic relation. And the trick is very much similar as what we used in the Jarotinsky equality case. Okay, so this is just the definition of the canonical distribution, the product of the canonical distributions, and then you see this. here you have this Boltzmann factor precisely. So if you put it here, you can bring this here. But from here, you have extra this one. So you have to cancel this one by putting it here. So, but what do you get? Well, here you simply get the product of canonical distribution. So the same distribution with x replaced by x prime. And here you have this. But with this symmetry, you can write it like this. So this is our basic symmetry. Very simple. Now, here's the derivation of the fluctuation theorem. We look at the probability density that the entropy production delta STX is exactly equal to this lowercase s, which is a real number. Okay, and recall that this x, the initial state, is distributed according to the canonical distribution. So this means that, of course, this delta STX is distributed probabilistically. So we can talk about the probability density that this quantity takes this value s. So this lowercase p of s is the probability density that the entropy production is exactly equal to small lowercase s, and it's given by this. Okay, x is, of course, distributed according to the product of the canonical distribution. And here you have the delta function. So you want to pick up the case where delta STX is exactly equal to lowercase s. Good. Now we use all these symmetries. This comes from the Liouville theorem. This is what we derived. This is just the definition, and this is the symmetry that we derived. Now, so PS equals this dx becomes simply dx prime because of the Liouville's theorem. This p notes p0x becomes this because of this one. And delta STX can be rewritten like this. Okay. And of course, since delta function is an even function, you can write it like this. Now, here, because of delta function, this delta STX prime is always equal to minus s. Okay, so this can be replaced by minus s, and you can put it out here. Okay, and then what remains inside the integral is just exactly the same as this. Simply this dummy variable x becomes x prime, and this minus s becomes plus s. So this is precisely p of minus s, and with this extra factor. Well, very simple derivation, but very interesting, simple, beautiful relation. This is called the fluctuation theorem. Okay. Oops. Sorry. This is called the fluctuation theorem. So PS is the probability density that this entropy production is equal to a real number S, and it satisfies this symmetry. What does it mean? First of all, suppose that S is large enough and PS is not 0. And then this means that since this is very large, okay, and then this means that PS is much, much larger than P minus S. So this means that S is positive and large. So this means that entropy production is mostly positive, and the positive entropy production means, of course, heat flows from hot to cold. Okay, we knew this, but this shows that it is very likely that heat flows hot from cold, not in the other way. So this is a sort of description of irreversibility. But anyway, this is not surprising because this is built in our initial state. You know, we started from this very particular initial state in which we couple two systems. We have two systems in separate thermal equilibrium with different temperatures. Okay, but interestingly, there is a symmetry. So if PS suppose that S is positive, so PS is non-zero. It describes the probability that this natural things happens. Then if PS is non-zero, then this tells you that P minus S is also non-zero. So this is interesting. P minus S, that tells you something weird. If this describes the probability that heat flows from cold to hot, but this is non-zero. But of course, it cannot be very large. So here's a very simple estimate. Let theta be any positive quantity, then if you look at the probability that this delta S dx is less than or equal to minus theta, then it's upper bounded by e to the minus theta. So of course, if theta is like 1, then this is e to the minus 1. It's not very small. But of course, theta is 100, then this is e to the minus 100. It's very, very, very small. Okay, how do you derive this? It's very easy. This guy, if you look at, since this is the probability density, this probability is exactly equal to this, the integration of PS from minus infinity to minus theta. Okay, and now I use this symmetry, the fluctuation theorem. And now this e to the s part is upper bounded by e to the minus theta, because s runs from minus theta to minus theta, minus infinity to minus theta. So this is upper bounded by e to the minus theta. So you put it out here. And then the remaining integral is simply the integral probability. So it's less than 1. So you get this. Okay. So anyway, so this tells you that heat sometimes from cold to hot. And of course, if you are looking at huge system with many, many particles, then this kind of probability of finding this heat flowing from cold to hot is very small. But if you look at, if we are looking at small system with large fluctuation, then sometimes this can be in some sense observed, at least in numerical simulation, and this symmetry is there. And it's a non-trivial symmetry, non-trivial interesting symmetry. I'm not going into this. I'm not going to go into detail, but just let me say that this is a very non-trivial symmetry. And this is not usually the case, but suppose that this PS happened to be a Gaussian distribution or close to the Gaussian distribution, and like this. So this is the average, and this is the variance. And in this case, you cannot simply write down an arbitrary Gaussian distribution, because this must satisfy this relation. If you plug this in, and then you see that this sigma and S naught should satisfy this non-trivial identity. So this poses very strong and interesting constraint on the possible form of probability density for the entropy production. Okay, so that's all for this part.